All right, well, I have to say thank you to Mohammed for inviting me to give a talk on something related to my research. I've been in a position here recently that my research has been something I do in the middle of the night when I can sleep rather than every day. So my name is Aaron Dotson. Do we have any passwords and stuff for the? Okay, the password is sewer for professional development credit. The way today's talk is going to go is I'm going to start off the talk and talk for maybe 15, 20 minutes, if that, and then I'm going to hand it off to Cameron Wilson, who is my master's student who's working with me on part of this. So I'll kind of recap. Oh, we changed the title. Sorry about that. We're going to recap kind of what the Water Sewer Challenge has done to date, what we're currently doing, and then maybe what we're up to in the future. So on here, turn this on. On here, the key players at this point in time are not those either. So we'll leave that alone. Right now, the two people that are working on a project are myself and Cameron, with some help from Martin Senek, who used to be a faculty member here at UAA, who's now a faculty member at University of Portland. So as you all know, to give some very basic background, water and sanitation is a global challenge. Generally speaking, this issue arises in Africa and a lot of Asia as being truly without water and sanitation. But here in the US, even though we show up on the map as being kind of dark blue of greater than 95% installed with water, and similarly with sewer, in rural Alaska, in many rural places at that, water and sewer is not a common thing. You may have alternative practices such as hauling your own water and hauling your own wastewater. One of the communities we worked with in the last phase of the Water Sewer Challenge is Kipnuk, a community of about 800 people out in the YK. They do not have running water and sewer in their home. All the water there is hauled by the homeowner into the home, and the sewer is collected or in a honey bucket shown on the side here, and that honey bucket is carried down the road to usually a honey bucket hopper where you dump the bucket, and subsequently that hopper is collected by the community and hauled out to the lagoon. There is toilets and a watering point in town at the washateria, but every time we were there, usually the toilets were out of order. So you just used people's honey buckets or some other situation. So this is a situation we're trying to improve upon, and if you were to consider installing pipes in Kipnuk, as you can see, it's a fairly wet environment. It's discontinuous permafrost. The cost of installing piped water and sewer in people's homes tends to be cost prohibitive. And with that in mind, alternatives were needed to be considered. So the EPA, in conjunction with the state of Alaska, funded the Water Sewer Challenge. I subsequently got some extra money that's ongoing from the National Science Foundation as part of the Food, Energy, Water Nexus with Fairbanks, where the Water Sewer Challenge system is part of it, in consideration with how to develop the Water Sewer Challenge system into the context of a dispatchable load, meaning if there was alternative energy like wind or solar in the community, how could the Water Sewer Challenge work when there's excess load in the system rather than just putting an overburden of load on the system. We've had a lot of people work on this project through the years doing this, from UAA to University of Colorado, G.V. Jones, Streamline AM, Southern Nevada Water Authority acting as our advanced lab, listing there's probably 15 undergraduate students, 5 or 6 graduate students, and a number of faculty. So it's had a lot of people involved in what UAA has been doing. So our premise, as the Water Sewer Challenge system is that to reduce the amount of hauling that people had to do. To do that, while achieving a goal, which the state set forth as 15 gallons per person per day, we needed to recycle water. So we decided that the bathroom sink, the kitchen sink, the shower, and the laundry Everything that went down the drain in those 4 fixtures would be recycled through a treatment system and returned to those fixtures. A subsequent parallel system for drinking water would be created, where you'd put drinking water in a container that technically that water should come from the washateria, as it's the local source of water that's treated to the regulatory limits, and that you would then disinfect it in case it had any contamination during the haul practice, and that would be dispensed to a separate spigot on the bathroom sink and kitchen sink for direct consumption. This drinking water system and the water reuse system has the ability to take water of the user's choice. Water comes in, gets either one-time past used for the drinking water system, or the water that comes in for user's choice would go around and around in this reuse cycle. In reality, when we started out, and our first version of the system with this is shown, is 35 gallons per week was needed to provide a household of 4 people 15 gallons per person per day. And even at 35 gallons per week, if you were able to keep rainwater wet throughout the entire year, most homes in rural Alaska, if you captured the rainwater, you could operate your water reuse system. For a toilet, we use a dry toilet system. This is a urine diverting dry toilet, very similar to what ANTHC has been installing as part of their pass. So we use the Separate. When I was on sabbatical, I helped ANTHC design their kind of Alaskan version of the Separate that LifeWater put together. So the dry toilet is another piece of that puzzle. And in fact, just to allude to what the future holds a little, the water sewer challenge, the next phase of it that the state just issued an intent to award, is kind of broken into these 3 systems. You have Summit Engineering that's looking at evaluating the dry toilet system across the state. You have Dow Consulting is going to be working on their countertop drinking water system with a membrane, a ceramic membrane in it. And then you have the UAA system, which is doing the whole water reuse side of things. So the future is on the horizon when the state awards the next phase of the contract. So what did our first demonstration system look like? This was a picture of Kara and Greg and myself out in front of our first water reuse system that was installed directly on the walls of the Connex. It didn't work out that well. This is what our mock house looked like, with a shower, a bathroom sink, a toilet, a washer and dryer combo, and the kitchen sink over here kind of in the corner, and then the drinking water system that you'd open this flap in the counter, and there's a bucket under the counter there. This house was automated to mimic what 4 people would do on a daily basis to use that 15 gallons per person per day. This is what our first version of our system looked like. This is what the second version of the system looked like after we ran the first version, found the problems, built the second version. This one was much more automated than the first one and much more compact. And then once actually the phase ended that we were doing testing in, I think, 2017, we had a system that could get about 15 times reuse. So every gallon of water that you put in the system could be reused about 15 times. That wasn't enough. And what we did find during this phase is that by adjusting our system slightly, we could overcome some of our underlying problems. So version 2's problems: we fouled cartridge filters way too fast. That's a lot of money. We fouled our membranes way too fast and they couldn't be cleaned. That was a lot of money. So how did we fix that? We went ahead and changed our system to have an equalization tank, a settling tank, and then a sequencing biological reactor. Something very simple to operate. It was on a daily batch, followed by a very, very basic cartridge filter to remove the residual biomass that would try to come out of this tank. Microfilter, and then the rest of the system was the same. So microfilter, that was a concentrating microfilter. All the waste from the microfilter would be sent back to the equalization tank for reprocessing. We had a reverse osmosis that would recycle its water from this tank. And then once this water became too salty, we would waste this water as concentrate. And then reverse osmosis, disinfection with UV light. And in our clean wash water tank, we would ozonate, mainly because this was our way to keep the total coliform count down and not add a residual disinfectant like chlorine, because most people in rural Alaska don't really prefer having chlorine in the water. So we were not chlorinating the water that was returning in the house. The bonus here is this went from 15x reuse to 40x reuse. So now for every gallon of water you brought home, it was used 40 times. So every gallon of water was worth 40, which was a big deal. This water's heavy. So in the summer of 2017, this is Greg doing one of our waste day cycles. It took 2 kegs of wastewater to get rid of the wastewater on a weekly basis. The homeowner would have had to haul those 2 kegs of water somewhere to dispose of it. Summer 2018, when we added that biological process in the front end, this is Tvetny standing in front of his waste cycle, which was 2 5-gallon buckets. Much easier to handle 2 5-gallon buckets once a week. So every week the homeowner would have to dispose of 2 5-gallon buckets of water and add 2 new 5-gallon buckets of water into the system. Process flow diagram, as we're all engineers in the room for the most part. Again, equalization tank. We started with this because of the fine dust and other things that are in the water. We wanted to avoid using a filter. So how did we do that? We let this water fill into this tank on a daily basis as the homeowner used it. Once a day, we would transfer that water into the settling tank. So this was empty, and the settling tank had a long time to settle. So we would settle here between 12 and 14 hours. And then as the equalization tank filled back up, this tank settled solids into the bottom of it. Through our 3 months of operation, we only ended up having about 2 inches of solids build up that you could just draw out of the bottom with by opening a valve. It would pump into the sequencing batch reactor, which was a fish tank pump, air pump, and it would just sequencingly add air. So it would go through a sequence of adding air, it would then settle, and then we would decant that tank with a pump. One thing that we had to be very careful of is we seeded this tank with wastewater biomass collected from Eagle River Wastewater Plant. That biomass was not prepared by any means to take the amount of soap that was used in the system, as well as the soap that didn't have really time to react with the biomass that's commonly found in a sewer system. So we still had trouble with foaming in this tank, but after about 2 weeks, our biomass became much more accustomed to the types of food or soap we were feeding it. And all the rest of the process of this, it was actually the same as our prior versions that you may have seen. So this is a picture of what bubbles look like when things get out of control. It doesn't take much with fresh soap that comes from our house to create bubbles. This was after 1.5 minutes of aeration. And so when we did our aeration sequences, the fresh water would come in after settling. We would do 30 seconds of air on, 1 minute or 2 minutes of air off. We would do that sequence for about a half an hour. Then as the bugs were able to munch away at the surfactants, after about half an hour, we'd go to 2 minutes air on, 2 minutes air off, and do that for another half an hour. And then after that, we'd go to full air on once the bugs had eaten all the surfactants. So where are we now? That system is still sitting out behind EIB. It hasn't been run since summer before last. We have been working with the Department of Environmental Conservation about the next phase. The next phase would be to finalize our design into a formal package plant type system that's fully automated. And that would be installed in the Templewood Apartments, which is one of the UAA dorms. So if you head down here to, the roundabouts near the Alaska Airlines Center, the dark colored townhouses are actually these Templewood Apartments. We would be taking over one of the garages. We would be putting in this system, replumbing the house a bit, having hopefully 2 graduate students and 2 undergraduate students live in that house, collect their gray water, treat their gray water, and hopefully get to the point where they're actually reusing the gray water in the house. It's currently under review by EPA's Human Subjects Research Review Board, and hopefully we'll gain approval to do that. We do have UAA's IRB approval. We're waiting on EPA's at the moment as terms of the funding arrangement it has with EPA. Things to know about this: the study is going to be trying to look at being very protective of human health. So the first phase of the study will be evaluating the gray water quality of the students. The second phase is installing the system, having that gray water treated, demonstrating that the treated water is of adequate quality. The third phase of that study is returning that treated water quality back into the home for the people of the home to use. So what's happening right now? One, we're waiting on EPA to give us approval. The DEC sent me in an email earlier this week that we're hoping to hear something back by February 2nd. But I won't hold my breath. It's been in EPA for a long time. Human subject research of this type is always quite challenging. But in this time, the state funded a secondary project that Cameron's going to talk about here momentarily. To answer the question is 15 gallons per day of water enough? And I say that because there was a lot of questions in the earlier phases of how much water is enough water. Troy Ritter did a great study with soap use in communities, looking at when the use of soap and water usage diverged, suggesting that there's water used for convenience versus water used for hygiene. And then there's the idea that there's minimum values that, say, the WHO and others use for how much water would be needed for health practices. So we were tasked with the next project. So I will leave this to Cameron, but since we're about 15 minutes in, any questions on the water sewer challenge at face value before we move into the technical issue or technical side of what Cameron's been up to?
Have you ever consulted any other use like the International Space Lab or somewhere where there obviously water is a shortage is a problem, and I imagine they have some sort of reuse system there. Have you ever looked at what they already developed?
Yeah. The space station has an incredibly complex process. One, because it has to work in zero gravity, but a lot of the general ideas are very similar. And maybe not to go as far as the space station, which runs into the problem where astronauts are required to use the water even if it's off spec. The ongoing research that is going on with regard to, I'd say, small scale water reuse is pretty large. The closest thing to the water sewer challenge that's out there in implementation phase or in testing phase is the Army has a project ongoing right now looking at barrack scale water reuse. And their water reuse train, the treatment train, is exactly the same as ours except for the front end. And so we're using a bioreactor, which is just suspended biomass or free-floating biomass. They're using a biologically activated carbon system. And so their researcher and I have talked a number of times about the differences between our two systems. One of the things that I have always been concerned about with a carbon type system versus a free-floating biomass type system here is I can program our system here to completely empty itself of all the water in it. And even if you end up with a small amount of biomass in a tank that freezes solid that you then thaw out, you're probably going to be okay. If you have a GAC column that is wet with biomass in it, that in the case of our system size and theirs, the equivalent column size would probably be about 15 or 16 inches in diameter and about as tall as me. So having a GAC column of that size that is damp in the Arctic that gets frozen, if you know about GAC and how water gets into the pores, you kind of turn GAC, which is granular, into PAC, which is powdered as the water freezes in the pores and destroys it all. So I'm more afraid that while functional, may have trouble here in Alaska. The other idea that we kind of allude to with the sequencing batch reactor is, say I decide that I'm going to leave my house in the winter and drain it and leave for a while and let it freeze. I could technically take all the biomass from my system, which is about 5 gallons, and go put it in my neighbor's house, if they have one, and just let them use my extra biomass for a while on, and then when I get back from vacation, take my biomass back out of their system. And so there's the ability that you can move the process around and keep it functional.
Was there any consideration to changing the type of soap that was used?
Yeah, we played around with a few types of soap, and we started another project along that idea. What we have seen is that some of the more natural soaps turn into more oil-based soaps, and so they cause very different problems. They may not create the same sort of soap suds, but then they harm our membranes. And so it's more of a balance of we have to kind of figure out how to handle both of those things at the same time and the broad array. And I think we struggled a little bit with the idea that could you really encourage someone to change their soap use dramatically? Or are they going to go to the store or Walmart or wherever and buy what is within their budget, not what we're telling them? But we did try.
The 2 buckets of waste per week, the second one or third one fall off.
These two.
Does that include the honey bucket waste?
No.
Family of 4?
No.
So that's a total different,
That's a different system altogether.
so this is the water cycle.
Yeah, this is just the water cycle. And that bucket, you can't really see it. It's a little sudsy in the picture here. Oh, sorry, I'm not repeating the question. Failure. The question at this point is, was the buckets of water shown all the water, or is it just the water reuse side of things? And as I answered, it's just the water reuse side. The word of warning is that when we had 2 kegs worth of water, that water was a little soapy, but it was pretty transparent. This water in the 5 gallons or 10 gallons of water that is still sudsy, this water looks like, I don't know, like a Hefeweizen type beer. It is this is not normal water in the same way. So it does look different than others. And if you leave it in a sealed keg or anything else for an extended period of time, it does become quite odoriferous. Anything else before I hand it off to Cameron?
As far as before the reuse water goes back in the system, is there some kind of online testing you're checking for E. coli or any sort of bad factors that you want the house to have?
Yeah, so the question is before it goes back into the system, is there any sort of testing to make sure that it's actually safe? So what we do in our system here, I'll show the slide of this, is there's a couple things that we do to test. There's no real online sensor for E. coli or microbes yet. There's a lot of microbiologists and others that have been trying for decades to try to come up with that, and I think they're getting closer. What we use, and we're going to propose to use in our on-site testing system, is in the treated water heading into the wash water tank. So before it even gets to the point where it goes into the home, because we could turn off, we usually pump this back into the house, and so if we turn off this pump, that tank is unusable, so up from the wash water tank. So what we would do is the water coming out of our reverse osmosis membrane through the UV is headed into here in the rinse water tank. We were going to be putting a turbidimeter and an S-can or something similar, so an on-UV monitor. So through those, we're going to gain kind of surrogate parameters to show that the water is of stable quality and that it doesn't have anything that is kind of a red flag. So turbidity has long been used in the drinking water industry to show that, and the S-can is just kind of the next step up that gives us a little bit more maybe a little on the biological side, somewhat on the chemical side of things. On the other hand, we also were able to do a couple other things. On both of our membranes, and really the only one that's important is the RO, we have a lot of information regarding flow rate and pressure. And so by monitoring flow rate and pressure, we can tell if the membrane stays as intact as we want. So if a membrane rips or tears or gets a hole in it, we would see a change in that membrane pressure or flow rate. And then the UV, these are home UV systems. They're not high-end with sensors on them. We monitor those by looking at electrical load. And so as long as the electrical load on the UV system is adequate, we've determined that the UV lamp is on and functioning for that process. Okay, so with that, I'm going to hand it off to Cameron. So Cameron, I'm handing you the mic and the remote, and you get to remember now to repeat the question.
Remember that in 15 minutes. Good afternoon, everyone. Thanks for coming. I'm Cameron Wilson. I'm started my graduate degree back in fall of 2018, and this is kind of what we're up to till now. So my project is the per capita water and fixture use in rural Alaska, and then the purpose of this is to answer some of the questions that came from what Dr. Dotson has been working on. So in rural Alaska, figure out how you want to put water in a village. One of the things you look at is the cold regions utilities monograph, and this gives you an idea of how much water is going to be needed to be put to each person within a village. And the way that they got this information was to look at how much the water was being produced by a water plant in the village, subtract any like industrial uses, if there were any in a village, and then divide that by the number of people that were served by that water. Now there's some problems with this. One of the main problems being you don't know how much you lost going to each individual house, and you're probably going to lose some water. And getting the information, we got about 59.4 plus or minus around 40% is what they're showing. Another issue with this is the date it was published back in 1996. This was 4 years after the Energy Policy Act was introduced, so a lot of which was implemented in 1994 and definitely didn't make it to rural Alaska. So a lot of these fixtures may have been updated, but they weren't captured. So the reduced amount of water wasn't captured with this number. So what my idea was, or our idea was, to look at water within the household to actually see where the water is being used and when it's being used. So this gives you some information or some insights. You get better water capita data because you know exactly how much water is being used in the house. And where I'm from, the south, pretty much every house, if you're on city water, has a flow meter going into the house. So you know how much water is being used per month, but that doesn't work here in Alaska. So using a flow meter going into the house and some other sensors that I've developed, we can pinpoint where water is being used, and we can also figure out how to focus your conservation efforts, like if water is being used most in one area. We'll also get black water and gray water volumes, and a kind of a bonus would be kind of hygiene patterns, since we know when and where. To do this, I look at a lot of some prior research, which is actually not too much in terms of doing this. One of the ways, or the two main ways I looked at going about it, it's bimodal. We can look at how much water is going into the house, and we look at where it's being, where the fixtures are being used. So one method they came up with was the NAWMS, which they have a flow meter and they have accelerometers placed on the pipes that are going to the fixtures in the house. Now this is within the walls, and it was just a tabletop type of experiment. And they got pretty good data, error less than 10%, but it's not exactly practical to tear into people's walls and put accelerometers on pipes to see where the water is being used. Another option was WaterSense, where they put motion sensors within the house to see where people were, and then they can correlate it with how much water is being used or when the water is being used. But there's also some issues with that. I was thinking if you put a motion sensor in front of a fixture and someone puts a water bottle in front of it, your sensor's out. You don't know that. And another issue they ran into was if two people are in the house at the same time and the two motion activators or two sensors are being activated at the same time, you have no idea which one the water is actually going to. So that was some non-intrusive methods. So I had a lot of constraints to look at. And one of them, especially for me, the Hawthorne effect or the observer's effect. And I definitely experienced this whenever I was testing it. If you're being monitored and you know that you're being monitored, then you're going to change your habits. So like testing some of these sensors at home, if the light's blinking at you, you're probably not going to let the water run while you're brushing your teeth. However, if it's not blinking, you probably will, even though you shouldn't. Some other constraints: it needs to be wireless. It needs to use alkaline batteries because I didn't want to have a pile of lithium batteries sitting on my lap going out on a bush plane. And these batteries needed to last for an entire year. I had some parts to work with, and so that kind of changed the size that I needed to be. And there was a lot of learning involved to get to this, had our Arduino clone to do all of the sensing, using a Raspberry Pi as our base station. Learned a lot of Python coding and even PCB design. And most of this coding and manufacturing was a lot of redundancy. So if I had remote access to these, if I accidentally shut it down, how is it going to turn back on unless I call someone and get them to turn it back on? So had a circuit that automatically checks every minute to see if it's turned on. If it's not turned on, it reboots it. There's other things like, did the email go through? We're trying to send the data back. If it didn't go through, okay, try it again every 5 hours until it sends. So all of these constraints and learning, this is kind of what I've come up with. This is the system setup, and I'll pass around one of my sensors here along with the amplifier that I've got. And if you'll kind of rub the piezo on the table, you'll see that the data comes up over on my computer, and that's what the Raspberry Pi is checking for. So I've said before, we have a flow meter going into the home. We also have a base station set up that is connected to the flow meter. That's where we install it inside the house. And then we have these fixtures, these sensors that I've zip tied to every fixture within the home. And it's getting the information, it's detecting vibration. And if you turn a fixture on, you can feel that it's vibrating or hear that it's vibrating. It's relatively low and quiet, so the amplifier amplified it by 1,000 times so that it could hear everything. And then if it's determined that the fixture's turned on, it sends a signal to the Raspberry Pi. So the way this is actually working is the piezo element is getting an analog signal, kind of pretty random what it sounds like. There's a lot of cavitation and noise from the aerator on the fixture. And what it does is I have multiple ways to adjust the sensitivity of it. I can, number one, if you'll see, I've got a little potentiometer that I can adjust to. It's a dual op amp, so one of them is a comparator. I can adjust the sensitivity or the threshold of where, if it goes over that point, it is considered a digital pulse, and that pulse is sent to the Motino on the sensor. Another way I can do this is I'm looking at it for 5 seconds, and I'm counting these pulses. If it needs to be longer, I can count for longer. If it needs to be shorter, I can reduce that. And then, what's the final way? I think that was it. So looking at these different fixtures, they all act differently. And the shower and the toilet it's on or it's off. So it's pretty easy. It's going to make a certain amount of noise. And as you can see that the toilet comes on, stays the same, shower turns on, stays the same pretty much throughout. But a sink is much more challenging because you can turn it on just a little bit, you can turn it on all the way. So that's one of the reasons I had to increase my amplification on this in order to capture these small, the lower noise thresholds. And I also had to make it to where it didn't pick up artificial background noise or some sort of background noise, because if I didn't do all of these, if someone was talking, it would hear it. So that's why it only looks every second, and then it has to be activated twice before it will actually say, okay, it's turned on. So once I got everything developed, I made 150 of those, 16,000 solder points. By the time I finished it up, made 25 of the base stations. Went out and installed them. We did 7 homes in the Norton Sound region, 5 homes in the interior, and then 7 homes in the YK Delta. And the reason we only had 5 homes in the interior is it is a massive challenge to find homes that have exposed plumbing and not copper in rural Alaska. So we weren't going to tear into people's walls to install these flow meters, and the flow meter needed to be installed horizontally, so that was another challenge. To get enough people to actually want to participate was another challenge, so this definitely took a while. And as usual, the technical turns out to be relatively easy. Getting people involved and working together is the challenging part. Here I'm installing it under the counter. That's, I forgot to mention, that's the non-intrusive part, or the observer's effect. With this type of sensor, I'm installing them underneath the counter, so you're not seeing it. The only one you're going to see is up on the shower head. I couldn't hide that one. So we've got all this data coming in, and the way I'm doing this, you've got these vibration sensors are feeding information into one file, so it's the node data, and it gives you a timestamp and what the frequency was coming from it. And then I've got another file that's being developed from the flow meter in the base station, when the water is being used and how much water is being used. And then each day I merge these files based on the timestamp, so I can see that, okay, at this time this much water is being used, the toilet was activated, so most likely that's where the water's going to. And then looking at all this information, we can process it and see that, okay, the toilet used this much, the sink used this much, the shower used this much within a day. For an entire day, looking at how much water was being used after processing this data, you can see how, in the gray, how much the toilet has been used and how much water the toilet's actually using each flush. It was definitely the main one for this particular day. You can see the washing machine was used in the afternoon, wash and then rinse cycle, and then you can see the shower was being used at the end of the day. Something interesting about the shower, looking at all of my information, was it was consistently about 14 gallons, and you would expect it kind of to vary depending on who's using the water. But since I installed them, I know that the hot water tank is about this high, so that you run out of hot water, most likely. That's the day that we're looking at on the previous slide, 8/6, and that's what the water looks at throughout the week. So it varies pretty wildly depending on, you can see some days that either people weren't home. I think one of these was on a Friday. No wash was being used. The toilet's relatively consistent, and the sink usage is relatively consistent. The shower, about one per day. So for this 30-day sample, 1.8 gallons per minute on the shower. It's relatively expected. 1.7 gallons per flush was probably a little high. 32 gallons per wash, which is way higher than what they were using for testing for the 15 gallons per day per person. So for this 1 year, or this 1 month, we got about 29.7 gallons per capita per day. So that's obviously way too high. So what if we reduce the washing machine? I said cut it in half. So they were using, 12 gallons per wash instead of 32 gallons per wash. Well, that brings us down to about 24.7, not quite there yet. Well, let's try putting in a dry toilet. Well, that was a definitely high impact, brought us down to 18.7, but still not quite there. If we did both, reduce the washing machine load and had a dry toilet, then we're already there. And that's just looking at 1 month of data for a 4-person home. So basically what we're looking at is, it's just looking at the 30 days is probably, with those two options, will work out. So what's happening right now, what I'm working on, is all the data analysis. And that 30-day sample, I did it manually going through Excel, which takes a while to scroll down through all of them. There are about 5,000 lines per file to go through and compare, and you can do some formulas to do it. I downloaded 2,000 files, and fortunately it was all through Gmail, so it was click, download, click, download, click, download. Also, I get 19 emails per day to go through, and by the end of the project, I'm going to have over 30 million lines total to process. So obviously not sustainable for what I'm doing now. So what I'm working on is some Python programming and working on cloud computing with Martin Sinek in Portland to automate this process, doing some more advanced things in terms of identifying events, which I'm hoping Martin can help with. And then I'm working on just going through and seeing how much water is being used per fixture, when it's being used during the day, when it's being used during the week, that kind of information. So there's some bonus info from this, which a lot of interest in. I'm actually presenting next week at the Public Health Summit on some hygiene patterns that you can see from this type of data. Just from this 1 month, I was able to see, if you look at okay, the toilet has been turned on, and then you can see at the same time that the bathroom sink's been turned on. Well, most likely that's someone washing their hands. That's what you would think. And going through all that manually, I saw that pretty much with the 4 people, 1 in 4 times someone was washing their hands every time the toilet was being used. So either one person is consistently washing their hands, or once a day someone's washing their hands. So that's kind of information we can actually get from this. All of this type of research, there's definitely a lot of future to it. Just doing through some regular research, there's some, not Kickstarter, but pre-order type products that are out there, like an entire water, or a whole home water flow meter that can shut your water off and kind of do some machine learning about how much water is being used at each fixture. I don't know what they're using for ground truth, and it's not available yet, but they're getting there. There's also some companies that are doing the gray water reuse. Right now they're only being used not for just like going to lavatories or wash water or going to a garden or something like that. So people are working on it. We're definitely making some progress here. And that's all I have. Any questions? Yes, sir.
So, maybe I didn't totally grasp some of your presentation, but how did you calibrate, or was your intent to calibrate the flow with the vibrations, or how were you able to? Did you have pipe size data, or?
So the question was, we're calibrating the flow using the vibration, or were we doing something else? We're actually not using the vibration to measure flow. What we'd have is a flow meter that we're getting 40 pulses per gallon. So we're measuring that separately from the vibration.
Okay.
The vibration is only to tell me that, okay, this has been turned on.
Okay.
This fixture is turned on. And one of the reasons I'm reporting the frequency is because if we have 2 turned on at the same time, I can get somewhat of an idea of how turned on the sink is, or with the toilet and the shower, it'd be relatively easy to disaggregate that, but 2 sinks turned on at the same time is going to be more of a challenge. And we have battery information also that's being sent.
These houses all had piped water that you tested?
Yeah, the question was, are all the houses that we put had piped water, and that was a requirement that we had to use. They all had to be on a piped water system and, of course, a piped sewer system. And one of the villages actually had a vacuum sewer, so we didn't know if that was going to be a challenge or not, but turns out it wasn't too bad. But having newer houses that had PEX was a challenge to find. And PEX we needed to have PEX. I wanted to have PEX throughout the house. We had to have PEX to install the flow meter. But the reason I wanted to have PEX throughout the house is because these vibrations can travel through the pipes and activate more fixtures than I want them to. So when I'm testing this at my house and Dr. Dotson's house, it worked amazing. But when I came into some of these houses where shower, sink, toilet separated by 2 feet of copper pipe, it took me a long time to reprogram and adjust the sensitivity multiple times to get it to somewhat work out.
Did you, the vacuum system, did you find any difference in the water consumption through the vacuum system versus domestic?
Question if there's any difference with the vacuum system. We haven't looked at that yet to see. That was the last one we installed, so I haven't seen how much of a difference there is between normal toilets and a vac toilet. I assume it would be smaller.
Where was that at?
Savunga. Yes, sir.
The age of the people, the 4 people in each one, as people go through life, there's differences. Have you been able to pick that up?
Question is, am I able to tell any differences with the different demographics for different people, ages? I did record all that information. I'm not sure I'd be able to tell exactly from the data itself, but we do have the information to disconnect that to see.
You know, in other words, you would expect a young family with young children need more
Mm-hmm.
and specific as that cycle goes on.
Yeah,
So as long as you've got the means to be able to record some of that in how the family's actually doing.
yeah.
Are you anticipating going longer in your study?
Our study is for 1 year for each village. Um, the big difference is we had some people that had 13 people per home, all the way down to 2 or 3. So looking at changes over generations is not something we're going to be able to see. But for the future, if we're able to use these vibration sensors as a ground truth and have machine learning, we may be able to possibly have some better data just going off the flow meter and the timestamps in the flow meter. So that's a possibility in the future to take these out and then look at it longer term, but not for this study.
You're using one flow meter per house, and using this vibration to separate out where it's in. Is there a flow meter that can be put on each fixture?
The question asking about using a flow meter for each fixture. We just have one flow meter per house, and it had to be rated to handle the pressure and not have any liability issues. That was actually one of the very first things that when we were trying to figure out how to do this, is like, well, let's just put a flow meter on every single fixture. Like, that would be awesome. But we can't take the liability of putting a uncertified flow meter on every single fixture, because if there's a leak, then that's definitely a problem. And the expense of having something like that as well, and having it powered, because this type of sensor only uses 25 nanoamps whenever it's asleep. So that's how I was able to get it to last for, it should last for up to 2 years on the 6 AA batteries. Yes, sir.
Did any of the houses have hose bibs on the outside, or is there any other fixtures that were problematic with someone using water from a source you're not monitoring?
The question is if anybody has anything that's not monitored, like a hose bib on the outside. All of the houses had a drain port that could be hooked up to a hose. So I had to make sure each time we installed it that it was before that point. We had one house that wanted to drill a hole through a floor and have a hose bib on the outside, but nobody else had that for the outside. We did have some situations to where, like, a washing machine was not accessible. I couldn't put a sensor on it. So anything that was unmonitored will have that in a category itself. Anybody else? Okay.
All right. Without any more questions, thank you guys.